I think today we're picking up on the material. Oops, I have to move over. I think we're picking up on the material for on the map estimation. How are the labs going? Have people been able to do all the lab projects? Okay, and so you've done the first part of lab. The exam's on the 18th. That'll be an in-class exam, and so are there any questions about how the lab's going? You all done it?
Yeah.
Not
We didn't try the last
assume there's more people coming along. They tend to get in here late.
We didn't try the last part, 7.
That's where you actually, okay, so that's kind of what we're going over today, okay? And we're going to talk about, so the next section is, okay, so when you get to the non-quadratic optimization, things get more complicated. So we've done the quadratic optimization. In that case, there's a closed-form analytical solution, but it's not useful because the computation associated with inverting that huge matrix is not practical. So then when you go to the non-quadratic case, there's no analytical solution generally. So but you can write down, but then there's an optimization strategy. So now the optimization strategies become a little different because, you can compute the gradient direction, but the thing that's different is that the line search in non-quadratic case is different. Because in the quadratic case, along the line search, it's just a quadratic function of the one variable, which is the step size along the line. So since it's a quadratic function of that one variable, you can calculate a closed form expression for that one variable. Because the solution to a 1D quadratic function is 1D quadratic minimization, the linear equation, is a very easy calculation, right? So when it's not quadratic, then that calculation of the line search is more complicated. It has to be solved typically in some numerical way. So, so I'm going to describe some of those, and I'm going to use it as a mechanism for introducing this concept of majorization minimization, which is pretty widely used, very popular these days. It applies to a lot of problems. So, and then later, the next thing I think we're going to talk about after this, I believe, although maybe I'm wrong, is the EM algorithm. Is the EM algorithm the next section? And the EM algorithm actually is based on the majorization the majorization minimization technique. So this sort of introduction to optimization will actually help us with the section in the next chapter, which is the EM algorithm. You'll get the basic idea of how the tricks involved. Okay? All right. Okay. So let me switch to the document camera.
Professor?
Yeah.
Can I ask you a question about
sure.
So last time you mentioned that there is this classic example of balls of different weights or the same weight and having one ball of different weight and how to find that using. So is that somehow related to that problem?
Hold on for a second. So I'm sorry.
So last time while mentioning compressed sensing example, you mentioned that we can weigh some balls together, and that was just a tangent reference to that sort of example you gave last time. So I was wondering if
balls? I don't actually remember that example.
For weighing some objects together rather than weighing them separately, and how that relates to compressed sensing.
Oh, are you sure? I've heard that description before, but did I actually say it, or did somebody else say that? Maybe you heard somebody else say it. I don't actually remember saying that.
I thought we were talking about the L1 minimization norm.
Oh, the L1 minimization norm. Okay, yeah. Okay.
I just heard the tangent reference to that example.
Oh, yeah, okay, in some other context.
In some other context.
Oh, okay, yeah, because I don't remember saying that, but I believe you. Okay, yeah, I've heard that example.
So I thought you mentioned it.
Okay, maybe I did, but I don't remember. Okay.
So was that in reference to finding a heavy or lighter ball? Because I looked it up next time, and then the lower bound for that computation is actually the same as binary search. So we don't get any gain advantage by doing computation.
Right, yeah. My phone is ringing, sorry. So there's a few issues there, but Well, first of all, but I'll tell you,
We can take it offline later.
yeah, we can take it offline. Okay, but, yeah, so the idea there is that with the L1 norm, you are kind of looking for, it's a convex optimization solution, which looks for the best sparse solution to your problem, right? And, it turns out that, there's kind of a related but different topic, which is that it turns out this A matrix we're using in our analysis, where we assume some general A. And it turns out that you might think it's good for that A matrix to be, so that if that A matrix is measures fewer measurements than we have unknowns, right? So if the matrix is wide and short and wide, okay, then you might think, well, it's best to just have measurements of the individual points by themselves, okay? Because then you have a pure measurement for each pixel. So it's a kind of a simple story, but it's not really a good story. It's better to measure all, sort of a linear combination of all the pixels together, because then it's easier to exploit information about the coherence or the distribution of the image. I mean, I can talk about this some more later, but it's a really common technique, okay? So, actually, let me just mention a few words about it, because it is a lot of interest these days. So, people may have heard about, like, you know, compressed sensing or whatever. I mean, so the idea is this, that if you have a measurement in a space, right, and if you know, so let's say let's say you have x1 and x2, right? So you have a two-dimensional quantity that you don't know, right? So if you're going to make a measurement, right? You can measure something about these. You might think that what you want the measurement to be, is that you would measure 1, 0 times x, right? So that would basically be just x1 plus some more, okay? Right? But that's not necessarily a good thing to do. In other words, intuitively, people usually want to measure a single pixel at a time, all by itself. But in practice, it may be better to measure a combination of pixels. Because let's say you know that x1 and x2 are highly correlated, right? Then the distribution is like this, right? So that in fact is often the case, because if x1 and x2 are two pixels in the image that are nearby each other, then you know they're highly correlated. So you're actually better off measuring something which is, you really want to measure along the axis of this correlation. So you're actually better off measuring a quantity which would be proportional to this distance. And that quantity would really be, we'll call that y, is going to be 1/2 times x, right? So the trick is this. So after you make this measurement, your uncertainty is sort of along this axis, right? The trick is to get the uncertainty after your measurement to be orthogonal to the this is the manifold that the data lives on, right? And the idea is this manifold could be sparse because it's thin. So often, one sort of thing to do so taking individual measurements of individual pixels, if I just measured one pixel, I would cut down, that wouldn't be nearly as good, okay, as measuring them both together. So, one sort of conservative thing to do is to just make random, to populate this matrix randomly, A. So just put random entries into A, and then you'll get sort of random projections of X. So, that may or may not be practical in an application. And if you design A based upon your specific knowledge of X, then you can do better than that. But that's sort of this idea. If you want to find, I think you want to find this lightest ball.
Right.
You measure them in groups. Because when you're measuring them in groups, what you're doing is instead of just measuring them one at a time, you measure them all together. So you actually get more information out of the system that way.
That example doesn't use sparsity approximation problem at all. So I shouldn't relate that to this.
Yeah, but it's definitely related. It's definitely related, okay? Yeah, I think you're on the right track.
Thanks.
So, Okay, so now, let's see. Okay, so in the general case, we want to solve a problem. I assume that you guys have read the notes, right? So you want to solve a problem. We have a function f of x y, which is the negative log of the probability of y given x minus the log of the probability of x. Okay. So so this is the map estimate. Minimizing this with respect to x is going to be the map estimate, right? So so now there's two. I mean, okay. The notes here are just reinforcing things I think we've talked about. But okay, this thing is a forward model. That's a prior model, and we want to minimize the cost function. Okay. Now the problem is, how do we go about solving this optimization problem? Okay, so we're trying to solve an optimization problem like this, okay? And right here, we're trying to minimize this function with respect to x. And so the structure of these problems is usually, there's sort of a standard structure to this problem, which is that first what you do is, okay, this is the algorithm over here. First thing, you usually have an iterative loop. You start at some initial condition, and then at a particular point, you find the direction of the optimization, D. That's the most important thing here. But you might also find an A and a B, where A and B tell you something about the interval over which the optimization is going to occur. Okay, so this is figure 7.2, and basically, you take the function, and at the current point, you find the direction you're going to do the optimization. So now what you have is you have f of xk plus alpha times dk, right? And that thing then is going to a function of alpha. Okay. So now what you want to do is you want to minimize this. Okay, so that you want to minimize this with respect to alpha, right? So if you plot this, basically it would typically look something like this. So this is alpha. And initially you pick the direction D. If the direction D is in the direction of the negative gradient, then initially you're going to go down at least. And usually you pick a direction so that, you wouldn't normally pick a direction D so that the function immediately goes up, okay? That wouldn't be so good. So usually it's somewhere aligned with the gradient, so that it initially goes down, but then if you go too far, it goes up. And the minimum point here we call alpha star, okay? That's the value of alpha that minimizes this cost function, right? So you want to solve this line search, but the problem is that this function may not be continuous. So the basic strategy here is you find the direction to do the minimization, you solve the line search function, and then once you solve the line search, then you update the state by adding the determined amount alpha star of the motion and direction, right? And then you just keep repeating this. Then the difference between different algorithms tends to boil down to how you pick this direction. If you're doing gradient descent, then the direction is just the gradient. If you're doing conjugate gradient, then that direction is the conjugate direction. If you're doing coordinate descent update, then those are just individual pixels, right? So now, okay, so then there's two places where, so this is generally not a huge amount of computation, just updating the image, okay? So most of the computation is usually either in the selection of the update direction and or the calculation of the line search. Now, if you're using gradient descent, then this is just the complexity of computing the gradient. Okay. So the line search is not always the dominant cost, but it's often an important cost. And if you have, like, say, a quadratic optimization, then the computation associated with the gradient is essentially, it's basically like, okay, so, okay, so this is the cost function right here. Then the gradient with, the gradient is basically, I should just calculate the gradient. Okay, so if you have an expression like y minus ax is norm squared, right? The gradient of that with respect to x is going to be equal to y minus ax transpose times minus a, right? So, so this is basically the computation here looks like the transpose of this is minus a times y minus, so this transpose is y minus a x. So that's equal to minus a transpose y plus a transpose ax. So this actually could be pre-computed once. Oops. But this is the part you have to compute online. So every time you do an update, you have to compute a transpose a. So in tomography, multiplying by a is a projection, and a transpose is a back projection. So typically, these algorithms, calculating the gradient requires that you multiply by a twice. So my point is that if you're trying to compute this function along this curve here for alpha, if you want to find the minimum of this curve, every evaluation of that function on the curve can be about the same complexity as it takes to compute the gradient. So if you have to actually search along this curve and evaluate it in many points in order to find the minimum value, the cost of this line search can far exceed the cost of computing the gradient direction or whatever other direction. I mean, these are kind of loose arguments, and they can vary a lot depending upon the particular application. But the bottom line is this: if you're not careful about how you do this, the computation associated with this line search can far exceed the computation required to do this step of actually finding the update direction. Okay, does that make sense? Okay. And what really this problem is that if you're doing the minimization of this line search, that it's very easy to see that the minimum here is at the bottom, but that's because I have the value of the function along all these points. If I don't know, then the question becomes, how do I figure out where the minimum is with the minimum number of evaluations of the function? It's like you're playing, okay, you guys don't know what the game Battleship is. Okay. You know the game Battleship? Okay. Oh my God, thank God there's some cultural connection here. Okay, so you know in Battleship you say, your battleship is in E22, okay? You go, miss, okay? So you're doing the same thing, but you're blind. I mean, I'm drawing this curve, but you can't see the curve. You just know there's a curve, and you think it initially goes down, but you don't know how big a step to take, right? So what you're going to do is, it's like you got your eyes closed, and you're playing, there's another game, it's called Pin the Tail on the Donkey, okay? You know Pin the Tail on the Donkey? It's where you put a blindfold on, and you have like, you have a pin. Maybe these days they don't use pins anymore because they're afraid the kids will put each other's eyes out, okay? You have something, and you have to walk over and try to stick it on the right place, okay? So you have this curve, okay, and this is alpha, and you're like, well, I don't know where the minimum is, right? So you know that the value of the function is this right here, okay? And then you calculate the next point, and you go up there, okay? So now you go, oh, well, okay, I evaluated it there, but I don't know. Is the solution over here, right? Maybe the curve went way down and it's coming back up, or maybe it's over here and it's still going down, right? So now you have to guess. So you pick some other point. You say, well, maybe I'll calculate it here. And you go, oh, it came out here. And you go, oh, okay, well, maybe it's kind of over here somewhere, right? But every time you evaluate one of these points, there's a huge cost to it. Because computation of the function at each of these points is the same complexity as computing the whole gradient. Right? Because you have to evaluate this function, right, f, this complicated function, with respect to a new argument. So, then the game becomes, how do I find the minimum? So maybe it looks like this. And the minimum is really here. How do I find the minimum to great accuracy with the minimum number of valuations of the point? So this is very important. Okay, so there's a few solutions. Okay. So one solution is we'll say, okay, so we have this function. Where's my notation here? I'll call it. So we have f of x plus alpha d, right? And that's equal to, that's some function, right? And we want to find its minimum. So one solution is this. You say, okay, I'll take the derivative with respect to alpha, and I'll define that function as g of alpha. Now, often you can calculate the derivative of this function with respect to alpha analytically, because what it'll be is it'll be like, well, you compute the gradient of f of x plus alpha d, right? And then I take the inner product of the gradient with d, and that'll be the derivative of this with respect to alpha. Does everybody see that that's true? Because if you're moving, if alpha changes a little bit, right, then you're moving, if alpha changes incrementally, then you're moving the value, you're changing the value of the argument of the function by in the direction d. So you take the inner product of d with the gradient, and that will exactly give you this derivative. So you can calculate that analytically, and that's d of alpha. And now what you can do is say, okay, well, what I really want to do is I really want to find the root of g of, this is alpha, and then this is g of alpha. Okay. So I want to find the root of g of alpha. The root of g of alpha is equivalent to the minimum, assuming that the function's convex. So how do I find the root? I still have the same problem where I have to keep evaluating the function. So one simple way is if I say, well, look, I'm sure my solution is between a and b. Now, why do I know it's between A and B? I don't know right now. You have to find some way of bounding the solution, okay? So, you know it's between A and B, and then you can, an obvious thing to do is take the point halfway between it and see what the function is equal to halfway between. Now, you know the value of the function, you evaluate the function at 2 points, the first and the end, and then you evaluate in the middle, and you say, oh, well, okay, if the new value is, so let's say the first value is positive and the last value is negative. And if the value you check in the middle is negative, it means that the solution should have been somewhere between the first and the middle value. Right? So now you can eliminate it, and you know it's here, right? Then you take halfway in between that, and evaluate this. You go, oh, well now I know that the answer has to be in here, right? And you keep repeating that. So the uncertainty, this is called binary search. The uncertainty of the interval is going to be, if you do n iterations of this, I should use the right letter here. How many, what did I define as iterations for binary search? I know I had a binary search here. Here it is. If you have k iterations, then the size of this, here's the binary search algorithm. It's in figure 5.7. So this just shows you start with A and B. So you evaluate the function as g of A and g of B, right? And then with each iteration, right, you first calculate the intermediate point, right? Then you look at g of c. Okay, so g of c is Oh, okay. In this particular case, we're assuming that g is an increasing function. So we're doing maximization, I guess. Anyway, so you check to see whether the g of c is greater than or less than 0, and then depending upon that, you make the interval either the left or the right-hand boundary, okay? But the bottom line is this. There's two very important things here. Okay, well, the first thing is really very important, which is that the uncertainty of the interval epsilon, right, is going to be less than I guess the absolute value of b minus a over 2 to the k. Because every time I do one of these interval searches, I reduce the size of the interval by a factor of 2. So if I do it k times, then the interval size is the original interval size divided by 2 to the k. So that's fine. Now, the second thing I'm going to tell you is extraordinarily important, but I'm almost certain you won't believe me, because I've not yet found a student who did. But I'm going to say it anyway, so that later, someday, when you have this problem, you'll say, oh, is that what you meant? Okay. You're not going to believe me, okay? Which is, if you use this algorithm and you just terminate, right? Let's say you run k equals, say, I don't know, some relatively big number, 10, okay? Then the uncertainty of the epsilon is going to be less than b minus a times 2 to the 10. And 2 to the 10 is a pretty big number. It's like 1024. Okay, so this is 1 part in 1,000. So it's an accuracy of 0.1%, right? Sounds pretty accurate, right? And then, so you sound like you're pretty good. If you do this, this doesn't work, okay? This will not work. I know you don't believe me. You're saying he's just kidding. I'm not kidding. What'll happen is that because when you're doing the update, you're quantizing this thing. You're not getting exactly the point at the minimum. You'll get stuck, and you'll get trapped in a local minimum. Okay. So the intuition behind it is this: imagine that you have like a very smooth glass bowl. Okay. And you put a ball bearing in here, okay? Right? And now let's say you put some jelly on it, okay? I'm trying to think of something that's not really sticky, but something that's viscous. What's a viscous material? I don't know. Honey. You put some honey, okay? But the honey's not dry. Okay, so it's not sticky. It's sticky, but it's not like glue, okay? It's just viscous, okay? Oh, I know. Put motor oil, okay? Really thick motor oil, okay? On here. Okay, what'll happen? The ball bearing will roll down to the bottom, but it'll get right down to the very lowest point because it's a nice, smooth, glassy surface. And the motor oil will, in fact, help it get there. Right? In fact, if you didn't have the motor oil, it would like go ding, 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 and it'd take a long time. If you put the motor oil down, it'll go, okay, pretty much go right down to the bottom, okay? That's fine. Now, what if instead you put like spray, so you put some, okay, so what if you get like some beach sand, okay, and you put the beach sand in with the motor oil, or you just get the beach sand like a little bit motor oily, okay, and you push it on the bottom, or you just sprinkle some sand at the bottom, okay. Well, what'll happen? The ball bearing will go over here, and then there'll be like a little grain of sand right there, and it'll get stuck, right? That's what this epsilon is. It's like a little grain of sand, okay? Yes, you can make the grain of sand really, really, really small. You can make it really small. But basically, theoretically, if you make the grain of sand like Armstrong, it won't matter, okay? But you have to make the grain of sand really small. okay? Or it will get stuck. The ball bearing will get stuck rolling down. If it was motor oil, it's fine. It can be viscous. So what you could do is the following. The motor oil is the following algorithm. Let's say you did this. You had epsilon star is equal to the R min over alpha, alpha star of f of x plus alpha d, right? And let's say instead you did this. You said, well, the new x is going to be the old x plus alpha star over 2 times d. So now what's happened is, let me back out a little bit. What's happened is, that's like the motor oil case. I've actually only moved halfway. You say, well, that's a lot worse than when I used this epsilon thing and I stalled, right? So in the epsilon thing, you do 10 searches, you get within 0.1%, but then you stop, okay? In this case, what you did is you calculated the exact right answer, and you only went halfway. But this thing, where you calculate the exact right answer and only get halfway, that'll be fine. That's like the motor oil. It may slow down the convergence, but you'll get there. But if you actually do this thing where you just stop, that's like a little grain of sand on the surface, and you're basically hosed, okay? You'll just stop because it'll get stuck on that little grain of sand. The reason is that when you do this thing where it's you're quantizing, you have discrete steps, and the convergence will stall. Okay, so how do you avoid that? The way you avoid that is that the last thing you do is that you take your final 2 points and you do a linear interpolation between them. So when you're doing this line search and you're solving this, you get down to the point where you have 2 points, this point A and that point B, right? And let's say this distance here is very small. It's epsilon, right? So it's, I don't know, equals 1 over 1,024. Right? You say, well, that's really small. But you can't stop there. You take like a ruler, draw a line, and select your final point to be here, being at the root of the linear interpolation between the 2 points. And that will get rid of this problem of the sand at the bottom of the glass jar. Do you believe me? Or do you understand what I'm saying here? So do this sometime. I actually have had some wonderful experiences with students where I've told them this and they didn't believe me and they thought, well, he's just kidding, he's just saying that to make me, he's just all just humoring, okay? And then they finally do it and they go, oh, yeah, it really made a huge difference, okay? So you have to do that. Okay. Now, but in general, this, this is called binary search. This binary search tends to be slow. Let's see, other thing. Oh, I know. So there's another thing, and this is, you're going to definitely want to do this when you do the lab. Okay, so you have 2 pieces of the optimization. You have the piece associated with the forward model, and you have, which it may include this blurring function. So you have this part here, right? And then you have this part here that's not quadratic. So when you're doing these kind of optimizations, you always like to treat the different pieces differently so you can appeal to whatever works best for them. So here, this is quadratic, so I can compute the first 2 derivatives of the update for just the forward part of the problem relatively easily. So I calculate those 2 things. So I can calculate the first 2 derivatives, I call them theta 1 and theta 2, and that's a simple quadratic expression. So I can simplify this function to have this form. This is exact because I know that with the first term here was a quadratic term, so it's exactly represented as a scalar quadratic function of alpha, which is a scalar. Okay. So this is exact. But now I've at least simplified the form of my optimization. So now what I can do is I can do a minimization. You can use golden section search to do this, or you can use the half interval method I just described because
I use the half integral method because it's a little easier to understand, I think. Golden section search is a little more abstract. In golden section search, you don't have to compute the derivative. Sometimes that's handy. But neither of these methods is really very good, honestly, because you still have to do a lot of evaluations of this. Let's say k is 5, okay, 10. Then you have to do 5 evaluations of the function. That means it's 5 times more computationally expensive than computing the gradient. So this value k almost is linearly proportional to the total complexity. And for a lot of these algorithms, a student was just running a problem. He ran it on 64 nodes, each of which has 16 processors for 24 hours, okay? So that's, what's 16 times 64? So 10 times 64 is 640. Excuse me? It's 1,020. So he ran his job for 1,024 times 24 hours. Okay. Per processor. There's a lot of computation. So you don't want to be wasting that much computation, right? So that k there is a multiplicative factor. K is 10, and your algorithm is 10 times slower. So that you really hate that thing, okay? So you're saying, okay, well, how can you do a better job with less computation? Well, there's these techniques called majorization, okay? Okay, so what's majorization?
Okay.
Yeah, excuse me?
Can I just ask a question?
Yeah, very good.
So this is half integral method, right?
Right.
So you know that you get the minimum cost at particular x, but still you move by this half distance because then you made an analogy so that it comes down slowly. But then what are the chances of getting it trapped into local minimum?
Okay, well here I'm assuming there are no local minimums, and I'm assuming there's a strictly convex cost function.
Okay.
If there are local minimums, okay, so here I'm assuming that this row function is convex.
Okay.
If it's not convex, then you can be trapped in local minimum, and that's a likely possibility. Okay, so it's impossible for most non-convex optimization problems to guarantee that you are a global minimum.
Okay.
There are exceptions. The common case is that you just can't. So it's more of like an empirical thing, where you just kind of show that the result I get is pretty good, and consistently it's the best I can find. So, but you can't usually guarantee that it's the best analytically. Did I answer your question?
Yes.
Okay. Okay. So now majorization. Okay. So now there's this other technique which is really slick, and it's called majorization. Okay. So, and it's a really important idea, and it's going to come up. Actually, it's one of the basic things that I hope you learn in this course because it's useful in so many applications. Okay. So, but first of all, I should say that the same method has like a zillion different names. So, in the interest of being fair, I wrote this long paragraph here in which I tried to go through and figure out like what the history of it is, because there's been a whole, in fact, even started here. There's a lot of different communities have rediscovered this technique. As with most really good ideas, it's been discovered many times, and you know, like I don't know if you ever heard, but the old saying goes that you always want to be the last person to discover something. But it comes up in a lot of applications. Okay, so now the problem is this: you have some complicated function, okay, and actually it can be multidimensional, and you want to minimize it, okay. So you're currently at some point, we'll call it x prime, all right? And now what you do is you say, okay, now the problem may be this, that this function is very complicated, so minimizing with respect to the argument x is hard, okay? So what you do is this, you say, okay, I want to approximate this function by a simpler function. A typical case would be you approximate the complicated function by a quadratic function. So you say, but now the problem is so I can approximate this function by another function that's simple, and then minimize the simple function, and then hope that the minimization to the simple function is close to the minimization to the complicated function, right? So I'm substituting one function for another. So I think in the notes I call it a substitute function. It also is called the surrogate function. Maybe, I'm not sure which terminology is more common, honestly, but I think maybe surrogate function is becoming more common. But I just don't like the word surrogate very much. I don't know, I sort of find it an unnice word. I don't know exactly. But anyway, whatever. You can call it whatever you want to call it, okay? But you're trying to approximate one function by another, okay? So the new function we'll call we call it Q of X semicolon X prime. And hopefully that's approximately equal to f of x. Okay. Now notice that Q is a function of x prime, so it's a function of where I start. In other words, I'm not going to use the same approximation everywhere. It's like a local approximation about the current point, and the current point is x prime. So now what I'm going to do is minimize with respect to Q, and then hopefully that's going to work well with respect to f. So in other words, I would say, okay, so the new value is going to be the arg min over x of Q of x semicolon x prime. And then that'll be my update. And hopefully that'll be good. So, now the problem is, it could be bad. Actually, by the way, the Newton method and Newton Raphson is very much of this flavor. So the trick is this. I can say, okay, I'm going to have a function and I'm going to approximate it. If I know two conditions hold, then I can be guaranteed that by doing this approximate update, I'm going to get something that is better in the sense of minimizing this function. This is the two conditions. The one is that the approximating function needs to be tangent to the true function at the current point. And the other is that it has to be a strict upper bound. And if those two things hold, then when I do the optimization, my new value here, I'll call it x double prime. My new value is guaranteed to be a point at which the true function is actually reduced. Why? Because these two values are equal, right? And then after I do this update, this is clearly less than that, right? And this is less than that. So I've gone down. Okay? So one upper bounds the other. Is that clear? This is a really simple idea, but it's very powerful. So I want to make sure you understand this. Is everybody clear on this idea? So the two conditions are this. You say, okay, first of all, that Q of x prime semicolon x prime is got to be equal to f of x prime. So the functions have to be equal at the current point, right? And the other thing is that f of x has got to be less than or equal to q of x prime, right? So these are the two conditions that guarantee that two things hold, and we say that, let me zoom out. We say that that q of x prime is a surrogate function or a substitute function for f of x. All right. Okay. Now, if that holds, then I think the picture I just drew. Okay, so these are the two conditions, and if that holds, then it's easy enough to show that the updated value of x has to be less than or equal to the current value of x. So repeated application of this surrogate function principle is guaranteed to produce a monotone decreasing sequence of arguments of values of the function, right? So that's really kind of cute. Now the other thing that happens is that often you can really take q of x prime, and you can really add any constant to it. It doesn't really matter. So in fact, it's really not necessary to say that these two functions have to be equal at x prime. Really all that has to happen is that there's some constant that if you subtract, and you can always make them equal by adding a constant. And then you just have to make sure that once you add that constant, the two functions are tangent. So really the more general condition is that, okay, so the more general condition, but the slightly less intuitive condition is this. That if, okay, so if Q is the original, this uppercase Q is the original Q plus any constant which is only a function of x prime. Then it's the case that you can always get the original Q by just subtracting off the value of Q at its current value and adding f of x prime. So I just led you down a garden path that was pretty, a lot of simple steps, but maybe it got confusing by the time you were at the end. Okay, so basically the picture is this. If you have, okay, so you have the original function, okay? And now you can have any function, okay, such that at the current point, we take this point and we shift the curve down so that they're equal at that point. Right? So basically what you do is you say, okay, Q of x prime is going to be equal to, so I have some function uppercase Q of x prime. From that, I subtract the value of Q at x prime, and I add f at x prime. So, and then they're always got to be equal. So if I evaluate this Q function here, if I evaluate the little q function at x prime, then this would be x prime, so these two would cancel and I just get f of x prime. So, go through, if this is not completely clear to you, read it, because what I'm saying here is extraordinarily simple. It's just that it may be unclear because I'm saying it up in front of the room. Okay, so, but the bottom line is this, you have this degree of freedom that you can shift the function around, and it doesn't really make any difference. So under those more general conditions, the general condition is that if you can find an uppercase function Q of x prime which meets the condition of 7.17, then it's a substitute function. It's a surrogate function because it must be it meets the conditions. It's got to be tangent and it's got to be an upper bound. But basically, if a function's equal to another function at a point and upper bounds it everywhere else, it has to be tangent at the point, right? But the picture is exactly here. This is the picture, right? Okay. That the one function upper bounds the other. Now, if the upper bound is, if it's not a very tight upper bound, then what will end up happening is when you do the minimization of the upper bounding function, you will take only a very small step, and then you'll have to do this update a lot. So the conversions could be slow. But the beauty of this method is you calculate an upper bounding function, and you find the minimum of the upper bounding function, and then in one step, you at least are sure you've done something good, okay? So this type of technique can be replaced the actual, the binary line search. And the computation for doing this technique requires usually just evaluation of the derivatives, maybe the first two derivatives of the function. So the cost of this is like one iteration of the line search for the binary search. So this is much less computation. It's much more efficient computationally. This is a lot like the Newton-Raphson method, where in the Newton-Raphson method, you guys probably have learned about the Newton-Raphson. Oh, we're out of time. Newton-Raphson method. But so Do I have any time? Oh, yeah. This is a lot like the Newton-Raphson method. It's a generalization of the Newton-Raphson method to optimization, is what it really is. So make sure you go think about that majorization. It's one of the things you'll learn in this course that will be fundamentally valuable for you in the rest of your analytical life, as opposed to your real life. Okay.